My name is Aisyah binti Azhar from the Mechanical Precision Engineering. Under the guidance of Associate Professor IR Dr. Meng, I will present about my final year project topic, Machine Learning for Industrial Gas Turbine Health Monitoring. 5 main sections will be presented, including the introduction, literature review, research methodology, results and discussion, conclusions and further recommendations. As the world proceeds into the 21st century, gas turbines are becoming more and more abundant. The GE's most widely applied gas turbine, the LM2500, powering more than 400 ships in 33 navies worldwide, has proven by its many applications. Foreign object damage, or FOD, is a major concern of gas turbine engines. FOD is simply debris of one form or other which can damage the internal components of a gas turbine engine. An advantage of a gas turbine engine is its ability to be removed from the ship for repair in a short period of time, by approximately 72 hours. Propulsion and electrical generation turbines are no different than aircraft engines, and the hazard FOD represents to the operation of these engines demands the attention of all personnel. Internet of Things, or IoT, changed the way condition-based monitoring can be completed. For example, a certain piece of equipment usually vibrates at a given frequency. If that frequency starts to vary or changes substantially, it could mean something is starting to fail or need to be replaced. Condition-based monitoring in maintenance is focused on preventing asset failures, downtime, and unnecessary practices by monitoring asset health to determine what maintenance needs to be completed and when. It can be considered essential to any predictive maintenance strategy. Overall benefits of condition-based monitoring includes increased asset life, reduction in collateral asset damages, increased efficiency in maintenance practices and management, decreased maintenance costs, reduction in elimination of unplanned failures, and reduced downtime. IoT and condition-based monitoring allows maintenance teams to anticipate a potential failure and take actions. The application of IoT technology on condition-based monitoring can reduce maintenance costs by up to 25%, cut unplanned outage by up to 50%, and extend the lives of machines by years. The aim of this research is to develop an operable model of a healthy engine for the automated network utilizing historical data of the General Electric LM2500. Multi-layer perceptron, or MLP, in artificial neural network, or ANN, is used in this research to obtain the non-linear relationships of system inputs to targeted outputs. A genuine prediction of when an industrial gas turbine will fail is also developed. Research in this area has received increased attention over the years, particularly in the applications of ANN. In a research MLP showed good performance in recognizing multiple faults in the components of gas turbine engine. Other techniques have been implemented for fault detection, including the applications of similarity-based modeling to represent the process behavior and principal component analysis for the study of model residuals. The LM2500 consists of two major modules, the gas generator assembly and power turbine assembly. The gas generator assembly, composed of gas generator speed, gas generator vibration, gas generator assembly inlet temperature, high pressure turbine temperature, and pressure compressor discharge. Power turbine assembly houses the low pressure turbine inlet temperature, power turbine speed, and exhaust temperature. The computational modeling software functions are supported by the MATLAB ANN toolbox. The toolbox functions include identifying the training algorithm, training and transfer functions, the types of input and hidden layers, the initial weights and bias values, and other mathematical analysis that results in accurate predictions by an ANN structure. 1 year operating data from October 2016 to October 2017 of LM2500 gas turbines are obtained. The raw data sets are filtered to noise-free and noise-corrupted. Before training and testing, the data were first normalized to 0, 1. Normalizing the data will make preparing simpler for different features to take on similar range of values so that gradient descent can converge more quickly. The MLP model was trained with 70-30 training testing. 4,382 datasets were used for training and 1,878 others were used for testing. For training, bad training data are used as the input, while good testing data are used as the target and produces network 1 output. For testing, bad testing data are used as the input and network 1 output are used as the target, producing network 2 output, which is the predicted output. The predicted output is compared with the measured output and used to generate residuals, which are used to detect deviations from normal behavior. In other words, this modeling approach aims to identify deviations away from typical fleet behavior. Residuals were generated by the formula Ek equals to y minus y bar, where y is the measured output and y bar is the predicted output. The optimal number of neurons in the hidden layer was determined by the mean squared error validation curve, which compares training with respect to number of neurons. The lower the mean squared error, the closer it is to finding the line of best fit, hence the better the forecast. The model is intended to be used in real time by continuously generating predictions for comparison with measurements as new data is recorded. Considering the model complexity and training computational efficiency, the model structure 10-20-10-10 was selected as the best structure among the other potential structure. The selected structure was able to provide the lowest mean squared error value of 0.0378 with 21 epoch or iterations in 8 seconds. Graph shows the mean squared error against the number of neurons. After filtration, 36% of the original data sets were retained. Using the trained model, predictions were generated after the standardizing of the inputs, and these results were used to test model ability for fault and anomaly detection. Figure shows 6 performance curves, typically used to assess gas turbine performance. Each plot shows the measurements and model predictions for the entire filtered pre-processed datasets. The measured and predicted output shows strong correlation in each of these plots, with only a very small subset of points falling outside of the prediction envelope. Figures compare measured and predicted sample number of T2 and T5.4 for an engine operating normally, illustrating the strong agreement between the model and measurements. Figure displays the T2 and T5.4 residuals and smooth residual signals for the engine during 1 year operation. Smooth residual signals are generated via a moving average with window size n equals to 20. For T5.4, a step change in the residual signal is observed around sample 2000 to 2500, followed by a return to normal operation. A decrease in T5.4 in comparison to the model prediction may indicate a reduction in the engine's capacity to generate power, which could affect the system operational readiness. As the low power turbine speed is not directly controlled but is established by the gas stream energy quantified by P5.4, entering power turbine assembly, accurate modeling and monitoring of this sensor is essential. The magnitudes and trendings of the resulting residuals contain more diagnostic information than the raw signals alone. Current remote monitoring and detection techniques for installed LM2500 utilize only raw signals with universal alarm thresholds, resulting in a significant number of undiagnosed faults and failures. The anomalous behavior detected through residual signals analysis illustrated the capabilities of the model for automating analysis. A technique for monitoring the performance and health of LM2500 gas turbine engines has been presented using a multi-layer perceptron regression model trained from 1 year operating data. The trained inter-engine model was used to generate predicted outputs from year 2016 to year 2017. Residual signal analysis was performed in order to demonstrate the effectiveness of the model in identifying anomalies in the fuel system and gas path. Vibration analysis and instrumentations corroborated by the failure history from the engine. A practical and scalable tool was developed for automated analysis of sensor data, reducing the hours required analyzing raw sensor data by equipment experts. Other ways to improve this work is by using other types of neural systems like support vector machines and para-consistent logic. Using the SVM approach, it is not necessary to specify the number of neurons in the hidden layer. The SVM can find the number of hidden neurons by itself during the learning process. Para-consistent logic is an approach able to process and treat unknown informations. Using this approach helps the problems with false alarms and noise in gas turbine signals to be reduced. Thank you.